This is one of my very favorite topics, and I know I say that a lot, but I really mean it this time. So I'm a thermodynamicist. I do a lot of this stuff in my own work, so I find it very interesting and very compelling. So the ideas here I think are pretty cool. They're also kind of challenging, so what I wanted to do today in this video is maybe take just a smidge more time, draw some diagrams to help you maybe get through this stuff. The first thing that I want to do is clarify the first law of thermodynamics. Okay, so it was introduced in the text. And here we're combining concepts of heating, work, and changes in thermal energy. So it's really just energy conservation. What we're saying here is that changes in the thermal energy come from two things. It comes from heating or cooling of our system, heating or cooling, and it comes from work. So this is defined to be work done on the system. So this is really a statement of energy conservation. So the first law of thermodynamics tells us that there are two fundamental ways to change the thermal energy of a system. I also want to point out that both of these things, Q and H, are processes. Now I want you to think about that. Thermal energy is something that a system has. It doesn't have work, though, and it doesn't have heating. Don't think about Q and H as things, think about them as processes. So try to avoid the word heat. I'm going to. Try to think more about heating and cooling. When we heat the system, when we cool the system. This is the result of heating or cooling. This is the result of the process of work being done on the system. Okay? So heat is not something that the system has. As you start trying to conceptualize these things, I like heating of a bar. Okay? So I like figure 11.17. I just kind of want to reproduce bits of it here. So figure 11.17. Here's what we have. Okay? We have a rod, some kind of a metal rod. And what happens is we heat one side. Okay? We heat one side. Okay? Again, the verb, the process of heating. And on this side, we put the side in contact with some ice blocks. Ice. Okay? So what happens is our system here is the bar. Okay, our system is the bar. And what we're going to imagine doing is a process where heat or heating happens, and that results in some energy change, QH. So QH is heating, and we quantify the amount of heating, that's QH. So we get this heating process, QH enters the bar on the left side. But what does the ice do? It cools the system. So we get some cooling where some amount of energy change, QH, occurs because of that process, some cooling. Right? And if that were the only thing that were happening, if there were no called irreversible processes, if no work is done, okay, then in this process, if the internal energy of the system doesn't change, then QH and QC are equal. Now, the way we're going to define these things is both these quantities would be positive, that's the convention. Okay? But that's a good way to start thinking about these systems. Okay? So, whether or not this is a real physical, and then we imagine QC leaving. Whether or not this is a physical system, a bar, a box full of gas, or some sort of conceptual idea, we're going to think about the heating and cooling in the same way. Now this leads us naturally into heat engines, things, devices, systems for which we get something useful out. Okay? So let's sort of sketch that as well. Okay? So the bar is okay, but it doesn't do a whole lot for us. So we're going to introduce the notion of a heat engine. And in a heat engine, what we do is we imagine that there's a reservoir, a hot reservoir somewhere, somehow, and a cold reservoir down here. Now these are reservoirs that can provide heating and cooling. Okay. Now we have some heat engine, that's what we call this thing. Okay. But essentially what we're going to be doing is we're going to be bringing in some heating, QH, into our heat engine. We're going to be getting out some useful work from that engine. And then what's going to have to happen here is we're also going to need some cooling, QC, due to our reservoir. Okay? So, this may be kind of hard to understand at first glance, but nearly every physical system that gives us useful work has something like this. It uses a thermodynamic process. Okay? There are some good examples in the text. When you think about a power plant, we often don't think about the cooling tower. You think about the power you get out. But in fact, in order to get any useful work out of this process, you need both a hot and a cold reservoir. You need heating of the heat engine, and then you need some sort of a cooling process. I'm going to try to clarify some of these ideas in class, but that process gives us some useful work. Finally, we're also introduced to notions of entropy, and entropy is very tricky. Okay? Again, I'm going to try to elaborate in class some more. One of the useful ways to think about entropy is as a measure of disorder of the system. What does that mean? I want to take a second and I want to give you an example here. I'm going to elaborate again on this example in class, but I do want to get you sort of primed up for it. So, when you think about entropy, think about the following. What we're going to do is we're going to start with, so I'm going to do two examples here. So example one, what we do is we take a closed box, we insulate it. Okay. So no heating or cooling from the environment. And what I'm going to do is I'm going to put a barrier here, and I'm going to trap a bunch of gas molecules on one side at the beginning. Okay? Now, this is a very ordered system. By that I mean, I know that everything, all the gas is to the left side. It's not over here. Okay? Now, the entropy of the system increases when I do the following. Let me remove the barrier. Let me just imagine I just get the barrier out of it. Well, what's going to happen? I think your intuition tells you that we're going to end up with a situation where I have the same number, 6, looks like I have 11, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have the same number of gas molecules, but they're spread out evenly. Now you might say evenly, that's less, that's more ordered, right? Nice and even. Well, it's actually not, okay? This setup here, this physical configuration, is what we call maximizes entropy. There are lots and lots of ways that I can get this set up. There are relatively few ways that I can get that set up, because I lose an entire volume over here. So this is a higher entropy state. And what we observe is that systems like to be in this state. It's very unlikely. And here's another way that you could think about it. Imagine removing the barrier and then watching the system over time. It would almost always look a lot like this, where I get a near even distribution of molecules. I would never observe all of the gas back onto one side. Processes evolve to try to increase entropy. That's what we observe. Another example, let's do a second and final example here, is imagine I had the same setup. I had a barrier up here, same insulated, and I have gas molecules of one kind on the left, and then I had an equal number of gas molecules of a different kind over here. I'm saying 8. Okay? What I'm going to imagine doing is removing the barrier. Well, what's going to happen? We observe the following. We observe that my blue molecules, 8, we observe blue molecules going all throughout the space available, and I also see them 5, 6, 7. I also do the same thing for the purple ones. They mix. Imagine taking snapshots in time of what the distribution looks like, where the molecules are. You will never observe this distribution again. And that the purple aren't going to magically sort themselves and the blue sort themselves to the other side. We just don't observe that. Now, there's nothing physically that's wrong with that. There's nothing in the physics of how molecules move to prevent that. But systems evolve to maximize their entropy. And that's what we see. I'm going to follow up on this idea. But this is a good first way to think about entropy. Okay. So, conceptually tricky. As always, come and chat with me, because these are going to be hard and maybe even new ideas. Okay, take your time, be patient, and have a little fun with it.